little virtual machine that runs atop different programming languages. And it's meant to be both the subject of a course on programming and also a tool you can use to script your applications in whatever programming language you implement this virtual machine in. The virtual machine is called B4, and this is an implementation that I've made in a language called Lil, Lil, that comes with Decker. And I just wanted to give a little demo because when you put the two together, it actually turns into a really nice little development environment for this low-level assembly language. And so this is the assembly language for the virtual machine. I'm in Decker right now. And so Decker is like this HyperCard inspired toolkit with its own little programming language called Lil, which you can see here's an example of what Lil looks like. I'm telling it on this screen here to load my module and connect some of the widgets that are on the screen. And then when the virtual machine does its thing to update the screen and update all these widgets. It's a live environment. You can move things around. You can visually move your little widgets around and drag different things onto the page. In fact, I'm going to add a little contraption here. This is something that looks inside of a particular register. So I can put this on the page, on the card, and then I can look at, say, the particular register with this name. There's 32 of them, so they have all the letters of the alphabet plus a couple of symbols. This over here is a set of scripts. It's like a little notebook of scraps of, in this case, B4 assembly code. So it's called B4A, and it looks like this. So the way it works is over here on this console, you can see the virtual machine has two stacks, the data stack, the control stack. So it's like a fourth-like architecture. It has an instruction pointer. And we can put some numbers on the stack. We hit Shift Enter to run it, and we get those two numbers. We can say add. That's one of the primitive opcodes in there. And you can see those two added up to 4. And so this kind of gives you like an interactive terminal for dealing with the virtual machine. The idea is that you build it on top of other languages so that you can script them. And so there's a language neutral test suite that tests that your implementation is correct. And so in order to implement that test suite, you have to provide this kind of like ASCII standard input output REFL so that the test can control it. And so you're guaranteed to have this kind of like textual interface to interactively control the virtual machine. Okay, so that's one of the ideas of the VM. And so you have these little symbols that you just have to know. Table of them here, and there's a reference of them here. I'm not going to talk about all this right now. There's a little canvas device you can add, and there's a terminal device. And so you can see that the way you script this is this colon turns on the assembler, and you've got, as I said, these registers. So the first 32 integers in memory are registers, and they act as a dictionary. You can use them to point to any piece of code that you want. And then the way the opcodes work, I know I'm jumping around here quite a bit, but the idea is that you can send text to the machine and it'll process it character by character. But then like internally, what it does is it has a bytecode, and these bytes they look at each one of those registers and they perform a call to whatever address is stored in that register. Whereas the next set of bytecodes take the same registers and fetch the data out of them and puts them on the stack. These take the data from the stack and stick it into those registers. So take one little number from those stack, put it in the registers. And these do like the same as the get, but they also do an increment. So they take a number from the stack, add it to the register, and then return what the register originally had in them. So you basically have this dictionary of 32 variables or whatever, and you're able to manipulate them in different ways. And that's like the bulk of what the machine does. So it's like half of the opcodes are just these 4 operations. And then you have a bunch of like little simple things like arithmetic. You've got logical operations. You've got some things to duplicate, swap, move things around on the stack, copy between the two stacks, move between the two stacks, read and write from memory, and then load from the stream. This reads from an arbitrary address. This reads from right after the pointer. Read byte, read integer, write byte, write integer, that kind of thing. These are blued out because I haven't decided if I'm going to keep these ops or not, but they read a byte, but they're signed. So read signed and load signed. And then you've got these control operations, like a jump to an arbitrary address in memory, a hop, which reads a short number and does a relative small jump. This is hop if the top item on the stack is 0, call, return, and then there's this next thing for doing looping. Does like an iterator kind of thing. And then these are all empty so that you can plug stuff into them. This puts a 0 on the stack, puts a 1 on the stack, and then these 3, this is halt. It's actually going to be start and stop, so it's going to be ST for start and stop. This is turn on the debugger, and this is do some IO to the standard output. And then these are like custom things that I've done inside of Decker. So the two bright ones are the terminal and the canvas. And the idea is that these will be there for every implementation, but Decker here only has these 16 colors plus some really cool like dithering patterns that you can use. They're all just black and white. And then the terminal, like in here, you actually can't do it like a read key because Decker has its own little keyboard. And when this is on, you can't see the screen. You can't have widgets responding to these key presses. But in other versions of this machine, you'd have the ability to actually just grab a key, and maybe in the console you have that a key was pressed. But in other environments, you might have a key down event and a key up event. So the idea is that these are like different kinds of hardware that you can talk to, and they're not part of the virtual machine. It's just maybe there's a protocol for talking to different kinds of virtual devices, right? So this is a virtual terminal and a virtual canvas. One other thing, and that is that it's designed around the idea of UTF-8. When you have a UTF-8 encoding, all of these characters here, they represent themselves. So that's the ASCII character set. And then anything that's not a simple ASCII character, you send like a multi-byte sequence, and it's always started with one of these red numbers. So the thought was that these would all be things that respond by putting numbers on the stack. And so you have one of these, and then you're followed by these little continuation things. So these are never the first part of a stream, and so then they're free to be used to send instructions. The idea is that this is like a calculator, right? It's not just a computer that turns on and starts running and doing stuff. It just sits there idly like a calculator until you tell it to do something. And you do it by, quote unquote, pressing a button, right? Obviously, it's not a physical machine, but if it were, you would press a button and you would be able to do whatever those buttons say. And since these are all blank, they're meant for you to extend it. And I just want to do a quick demo. I've already run this, so I'll just run it again from the start. So this means reset, which means clear the stacks. And this is a view of memory. And if I hit this button, you'll see it's all wiped out. These are all zeros now. And yeah, so I'll clear this, and then we'll start over again. So those are the two buttons I just pressed. And then we can assemble one line at a time. And when I hit Shift Enter on this, I've got this set up to send the text over here or to the virtual machine and have it run through the little interpreter here. So I run that, and you can see that the clearing did not fix that. So I'm going to put the letter S on the stack, and I'm going to run the terminal op, and that's going to clear the screen. S is for clear screen. There we go. Anyway, but what you see here, I ran this line, and what it did, so first of all, the registers are stored up here in memory, so they're all up here. And you can see that they're mostly 0, except a couple of them have things set up in them. And if you want a clearer view, you can say, I want to change this register to register E. And you can see that it's set at 100. This is saying the instruction pointer is at, not 100, it's 256, but these are all hex, so 100. And then this line has bound in fact, if I clear it again, let's just run this again. I don't have this set up right. I need to get this set up to a few things, but I say before register 1. Sorry. I'm going to have this set up so as soon as you drop it on the page, it becomes reactive. But right now, I've got to, let's just call this reg1, redrop. This should happen automatically. This is a work in progress. But the nice thing about it, the system is it's very customizable. Decker, I mean, you can drag whatever you want. It's all live. I'm building the development environment right in front of you. Okay, so now it says E, and hopefully if I run this now, yeah, so you can see it responded in real time by setting that to 256. I don't yet have it going the other way where this actually sets the value. But so these are like variables, right? So now we have like a function pointer pointing at this line that I just assembled. What does it say? It says load a byte, the ASCII character E, and then invoke the terminal op. So the terminal is this thing I've added to the machine. It's not part of the spec. It's just something I've added. And then that's going to emit one character. And then when we're done, we return. So now, again, I can call this to clear the screen, which is already cleared. And if I type this, and I can do it in batch, and you see there's a bunch of numbers up on the stack. So this is HELO in hex. And as I go through, I can just, again, type Control E, and we'll emit them one at a time. And the terminal device is running the emit command and executing it. What is the terminal device? It's just another contraption that I made in Lil. It's this thing. We've got a little font over here. This is the base 64 encoding of that font. This is a snapshot, so we can copy and paste, and so it's not slow. This is the cursor positions and whatnot. And then it's got its own little script, and it does all that. And so somewhere in here it says op E, and so on emit. So this is the character index. Pop it off the stack, make sure it's a byte, and then get the values out of these two widgets over here. One of these are the cursor position, and the other cursor position. And then it copies the character from the font. So I just made this in Decker, and it's a pretty short amount of code. And anyway, so that's it. That's what we do to print hello. Here's a loop, the same emit command, and then here's a loop that's going to print the alphabet. This is the assembly length. These are like little 2-character assembly codes. And so this says assign the A register to whatever we assemble on this line. There's like a pointer going around. So it's pointing at this address when it starts. The pointer is actually called underscore. And you can see that after it assembled all this, we're now pointing at this spot. So 104 is right here. So it's pointing right there. In fact, if we type 104 here, we have a little editor register. Okay, great. So what does it say? What I'll actually do is I'll run this. I'll comment this out, and then I can call this backslash. And if I run this, it's going to run everything that I've got here. So it's going to clear everything. It's going to define these two things. And then you'll see like a little bit more here as it defines this. Boom. And so now you can see the disassembly of whatever I've written here. And what we're looking at is we've got the same thing, load byte, E, run the terminal command, return. So that's one thing. And if I give these names too, I can also say emit. And I maybe call this main and run it. And then we'll get little labels down here. I can see that's emit and that's main. It doesn't know the registers yet. Maybe I should add that to up here. So switch this over and you could browse the registers in this little list thing. This is also just something I made in Decker. It's a canvas component and a bunch of fields and a grid widget. So the grid comes with Decker and you can just assemble things very quickly. This is also a grid right here. This is a grid that maps these names to whatever's in this text. And then this is a field that is just showing whichever one you clicked on. Got buttons up here. When you click on this, you can just add whatever widget you want to the page. And it's just these, and then what you can make your own out of these. Contraption. This is also a contraption to navigate between the pages. All right, enough rambling about that. So if we look at this main code, this right here is telling us where to put the instruction pointer. So the instruction pointer is actually already at here. It's in calculator mode. It's not doing anything. It's not running. And so when it sees this, it knows to assemble that as the assembler is running and putting stuff into the virtual machine's memory, it says, oh, okay, I see. This is where I'm going to set the instruction pointer. And so now I can just start stepping. But before it did that, it ran these directly. See, they don't have a colon in front of them. So lines that don't have a colon are executed directly. And so this one said, okay, just put this byte. Interactively, you can just type a number and it goes on the stack here. This is just another Decker field, but whenever you type Shift-Enter, Decker has an event that's called the run event, and you can do whatever you want with that. So you can either Shift-Enter to run the entire text of something, or you can highlight something. All right, step through this and see what it does. Well, let's just run it first. So we can say, hopefully we can say this. We can say control backslash, and that should say just run it. And it does have a return at the end, so it should just run. And the idea is this should print the alphabet. So what it's doing, and maybe we'll step through it again. Maybe put a new line down there. You can't see the cursor, but oh, all right, because I haven't done it yet. So we would say, what is new line? This is new line. Oh, I didn't write in little anything that handles the new line characters. All right, so there we go. And then you can't see anything that happened there, but that moved the cursor down here. So it says, so these are all just, again, the terminal ops. And so they're saying load a byte with some letter on it and then run the terminal op. And so now I've broken it down into different names. So TG is go to a position. TA is the attribute, which is a byte that has a foreground and background for these 16 colors. Read a key, which does nothing here. Like in a console, that would work. Whereas here, there's no interactive key press to or anything like that. Clear the screen, clear a line, and then fetch the cursor position. So fetch the cursor position, add 1 to those X and Y. So add 1 to the Y position, constant 1, add that. We can do it. We can run it now in real time. So if I run EC, it's saying we're at 0, 1, so we're right here. Underneath this A, add a 1 to the stack. So there's 0, 1, 1. I'm looking at this right here for the stack. If that had been 0, 2, 1, it would now say 0, 1, 2. But obviously 1 and 1 are the same. Oh, I didn't add. All right, so add them. Now, okay, we're going to drop the X coordinates because the X coordinate is saying we're here, but we could be way over here. So again, swap, zap, and now put another 0 there. It'd be saying we're at the start. And then now it says 2, 0, but we want to be at 0, 2, so we can swap, and then terminal go to, and there we are. And then obviously we return. So you can step through it just by highlighting a word and shift enter, and you can like step through your code that way. Or you can do what I was going to do in the first place, which is just say step. So let's go back to the alphabet, and we're stepping through this code because main is at 104. 104, that's this red symbol right here, or the red background indicates that's where the instruction pointer is. Then we're going to say, okay, put a 0 on the stack. Now, this does not disassemble quite the way I expect it to, because there's two ways to look at it. Sometimes you want to see the ASCII character, and sometimes you want to see what the corresponding instruction is. So I'm trying to make it a little smarter, but I haven't gotten that far yet in this version of the debugger. So anyway, right here, this says put this 0 into the letter J. So the J is going to be the loop counter for this loop that we're doing. Now, we're going to load the byte 1A, which is, so 16 plus 10 is 26. So that's the 26 letters of the alphabet. And then if I change this to J, we can watch what's in here. It's at 1A because it's looped through this the first time. So now when I hit step, it's going to be 0. I'm going to take this 0 and put it over right here. So the 0 will come off the stack. Boom. The 0 is gone here, and now the J is 0. We're going to load a byte, which is Control Z over here, but it's actually 1A, so 26. I guess that makes sense. So that would be the number letter Z or Control Z. So there it is. There's 1A on the stack. And now this is going to push it to the control stack. So the control stack is where the return address is after when you're returning from a function, you have to return to somewhere. And so that the control stack is going to record that. But I called this as a function. The address of where to come back to would be on the stack. But since I'm just stepping, right, it's as if we started at the top level running this code. All right, so we moved it to that stack, and we'll restore it later before we return. The next is going to do that. Okay, we've loaded the byte, and this is the letter A, because what we're gonna do is we're gonna add J to, so it's gonna be as if we're writing letter A plus this number. All right, and then we're gonna add 1 to J. We're gonna add 1 to J, so this is like J++ in C or JavaScript, right? So this right here is going to take the constant 1, put it on the stack, add it to J, and then return what was there before. So, boom. And then we're going to invoke E, which is the emit word right here. And if I hit step here, so I've actually redefined it again later in here, but it's the same thing. Now you can see the instruction pointer is at a later redefinition of E. And it just loaded the byte E on the stack, and it's going to call the terminal to emit, and we should see an A up here. All right, so there's the letter A. And then it's going to return. So then the word next is going to take this 1A and reduce it to 19, and it's going to count down. It's going to count down, basically. There you go. When it gets to 0, then we move past. We remove past the end. So there's a macro here. It's for and next. And so the for compiled to take this number and push it onto the control stack. And the next does the loop thing. This n compiled to the nx instruction. And what it does is say, if this counter on here is 0, then move forward. Otherwise, reduce that counter and jump back to by this amount. To do a hop backwards by FA, which is negative something. Okay, so that's it. That's the loop, right? And if I just keep pressing it, you'll see it's jumping around back and forth. And you can see it's temporarily pushing the return address up here, and then boom, it returned, and so on. And you can watch it run. You can actually step over the steps to each return statement, or something like that. Then we reached the end, and then we had an error because we tried to return without having anything on the control stack. That's it. That's what this looks like. It's cryptic, but you do get used to it. Here's another one. This just has, here I've got a string of 10 letters that say ANSI color. Yeah, so it's going to take this character right here, or this number right here, and we're pushing them onto the stack. There's no hole in here, so this is not being assembled. Only these were assembled. I cleared everything. I reassembled these things. And then in interactive mode, it's saying, okay, clear the screen. Boom. Set the color to white on blue, for is the blue color in ANSI color codes. And clear the line. Now, okay. Write the string. Here's W. This is another loop. We're setting R to the address of the string, and then we keep incrementing with C1 plus, 1 plus R, 1 plus R right here. So the first plus is to fetch this number and then move forward. This is the length of the string. And now we've fetched it dynamically, and we do another for loop, which is again pushing it to the other stack, doing a loop, and then returning. And so I'm not going to step through this. I think you get the idea, right? Go to position 2-2 and then write these colors. So these are just some colors that or some names I gave a long time ago. I might have taken them from a bulletin board system or something like that, but I standardized on these. Some code I was writing in Pascal in the DOS days. So it's black, red, green, yellow, blue, magenta, cyan, white, and then capital gives them like a lighter color. So that's these. And same thing here. I don't think there's anything much different here. I think I just rearranged that same script. I put the word hello up there. Okay, so now I wanted to. This is what I wanted to show really, and then I'm going to wrap up real quick. I don't think I'll go through all this code too much. Here I'm setting a buffer, so basically I'm using b as a variable that points to a string that has not been defined yet. B is the 63 byte buffer with a length byte at the start. So that's the first 64 bytes. And then C is going to be the first byte of the string. So it's a cursor in that buffer. C for cursor. So if I run this, it's just going to be empty. These are all zeros. But the effect of that is that it's moved the underscore character. So you can drag as many of these as you want on here, but we moved it to 140. So we're actually right here. You put a little button that says like move that there or whatever. Ed or something that moves. So this is the right pointer now. All right, so then we're going to assemble all these things that do the terminal operations that I just mentioned, and then space and new line. Boom. All I did was just compile those. They all have colons at the start. This is a library that does some printing for hex. So you can see that these are the hex digits. This says start the assembler, and then this says resume the assembler at the same place. You can actually put a number in and say jump around and assemble wherever you want. This is going to say emit one hex digit, just and make sure it's the number 0 to 15, and then fetch this, add those two numbers together, and read the character and emit it. This does it twice for the 2 bytes, the 2 characters of a byte. New line, N1 puts a -1 on the stack. It's just load short, -1. And then this is a longer thing that that loops through and does a bunch of shifts so that you can draw a multi-digit number. All right, this is an op table. All it's going to do is just compile a bunch of strings into memory. And these are the names of the opcodes. Maybe you see where I'm going with this. So now we can dump some memory. So if we want to look at what's in memory here, we can run this. And so this is the onboard version of this thing right here, this little debugger. It's a start on it. And so it's printing out like 16 bytes of memory at each step. And this is where we're using the multi-byte. We're showing the hex labels and whatnot. And I just happened to tell it to draw a particular address here. If we want to see the code for show mem, we could change it to show mem. And that this $sign basically puts that number onto the stack, the address of show mem onto the stack, so we can see its code itself. Not much to look at, really. you can see it does so exclamation point A, the one that sets A, is actually renders as this byte right now. But it's not smart yet. It doesn't know when to show an ASCII character and when to show they compile the same byte, and it's just depending on context whether it's data or code. So anyway, this here you're seeing that rendered here, and so you could compare and contrast if you wanted to. I don't think it's necessary. It's also shifted a little bit because we didn't start at a clean boundary. Anyway, we'll go back to 100, or again 356. So then the neat thing was this. So now I wanted to start on an editor, and that's why I left this 64 byte right, not really quite at the top, but at the top right after all the registers. I'm gonna go ahead and run this, and what you're gonna see is this editor up here. And this is what I thought was really cool. Like, I got to this point yesterday, and I said, oh, okay, I'm ready to make a demo, because I've got to start on an editor. I've got this is telling me go to the first character, so take the buffer address, add 1, and set the character or the C register to that. Right? So this whole line is one thing. And so if I type 20 over here, nothing's really going to happen. But what it is, it moved that pointer. And then I'm drawing it, right? So I'm using these same terminal primitives to draw the thing. And now if I want to say insert M in there, right? I guess I'm writing the word magic here. And you can see that it's on every time I run something, it says get the labels and call a label named. If I've defined a label in here, which I have down here, then as soon as I run anything, it's always going to update that. So just like these are live updates, the virtual machine itself can respond to events in Lil. So this makes a really nice live coding environment for the virtual machine. Anyway, so let's finish this. I did this, and I was like, okay, I'll move here. And now I want to insert another character at the start here. So right before this, like, how do you do that? You have to shift all these things over. I haven't implemented that yet. I was like, man, I wish I'm writing this code, and you can see I've gotten used to reading this code. This is perfectly intelligible to me. It's an assembly language. You get used to it. But man, what I want to do is I want to have a loop that moves this C here, and then moves the I here, and then moves the G here, and then A here, all the way up to where the cursor is. And that would be like a line of code in J, or in fact, it is a line of code in J. Probably shorter than this in the J version. I have to do, I'm at such a low level here, I have to do this by hand. What's the right way to do it? And I wish I could see this stuff. And that's when it occurred to me that, hey, man, I can just draw this thing. I don't have to visualize it in my head. I can draw the cursor here. So again, if not that you would have remembered everything I said here, I don't expect that because it's just a flow of information here. But hey, put a 0 on the stack, duplicate it, and then go to. So that puts the cursor right here. Black on blue, right? That's the attribute. Put the character from the buffer. So you can see here it's the control E, which is the number 5, right? A, B, C, D, E. Control A is 1, control B is, and so on. And so it's saying the length of the string is 5. And then we're reading it out of memory there. So I did that. And then I've already done this drawing for the memory that I was working on. So I just do that again. I take the buffer, add 1 to it, and then draw 16 bytes, and then draw a new line. And then clear the line, and then draw the cursor position. The cursor position is an offset in memory, so I take the cursor position, subtract the buffer position, and then multiply by 3, because these things are, we've got the quote and the space and the letter. So multiply by 3, and then add 1, and then go to that position, and then set the cursor color to the opposite of this, and print the caret. So there you go. So anyway, I drew this, and it's okay. Now every time I do anything, I can just immediately, if I want to go forward, well, I just highlight that word, and I hit Shift Enter, and it moves forward. If I want to move the cursor backwards, blah blah blah. And so I've got a live programming environment for assembly language on this virtual machine, and I feel like I've reached a point now where this is like really cool. So I'm going to be packaging this up fairly soon. I do want to finish this little editor, and there's a couple other things, but the idea is that you could use this Decker environment. It'll have the reference and everything in it. You can download this as a web page, save it to your local machine. You don't have to install anything. Write your code for this thing, debug it with all these little tools here in this live coding environment. And then when you're done, you'll be able to just grab the memory. I don't have an example of this, but you can see the basics for encoding of this data right here, where you get something similar for the virtual machine's memory itself. I gotta go. And stick it into Python or something, and now you could have your same code running in Blender or whatever, running on a web page in pure JavaScript. I do gotta go. Put a link in the description for where you can get all this stuff, especially after it's ready to go. And thanks for watching, and I'll talk to you again soon.